This is Professor Ann Orion Spehar from the University of Alaska Southeast, and this is a lecture on economic growth, the Solow Growth Model, Part 1, Capital Accumulation and the Steady State. Our course now turns to a much larger issue in economics, the determinants of growth over the very long term. We now ask what makes a country grow over time and across countries. Why do some countries develop and others do not? We focus on the economic determinants of growth, meaning that we will not discuss the development of the scientific methodology or the historical growth of commerce or the impact of the Cultural Revolution that took place during the Renaissance. Rather, we will focus on the economic determinants and focus for now on the factors of production, on savings and investment, and later technology. What causes an economy to grow in the long run is one of the most important topics in macroeconomics. But first, let's consider our learning outcomes for Parts 1, 2, and 3 of Economic Growth 1. After the student has completed this lecture, they will be able to, in Part 1, describe and model the Solow Growth Model in a closed economy. Describe the determinants and process of capital accumulation and how a steady state is attained. In Part 2, the student will be able to explain how a country's standard of living depends on its saving rates. Apply and derive the golden rule to the growth model to determine the optimal saving rate and capital stock. Describe the transition process of moving the economy to the golden rule steady state. And in Part 3, the student will be able to explain how to expand the Solow model to include effects of population growth, and explain how a country's standard of living might depend on its population growth rates. This current lecture is the focus of Part 1. So growth is clearly associated with increased life expectancy. It's also associated with lower infant mortality. 20% of infant mortality occurs in the poorest one-fifth of all countries, while 0.4% occur in the richest one-fifth. Raise the standard of living and we lower infant mortality. In Pakistan, 85% of the people live on $2 a day. In addition, poverty is associated with the oppression of women and minorities. And we also know that in higher income countries, women have fewer children, so growth can even address overpopulation and the problems associated with it. And it's also important to note that 1/4 of the poorest countries in the world have had famines during the past 3 decades. Economic growth raises living standards and reduces poverty. And anything that affects the long-run rate of economic growth, even by tiny amounts, will have huge effects on living standards in the long run. Consider an annual growth rate of income per capita at 2%. This will result in an increase in the standard of living after 25 years of 64%, after 50 years, 169.2%, and after 100 years, 624.5%. Now consider an annual growth rate of income per capita at 2.5%, just a 0.5% increase. This will result in an increase in the standard of living after 25 years of 85.4%, and after 50 years, 243.7%, and 100 years later, 1,081.4%. Growth matters, and even small growth rates matter. We are going to focus on the Solow model. Robert Solow won a Nobel Prize for his contributions to the study of economic growth. This paradigm is widely used in policymaking and is the benchmark against which most recent growth theories are compared. The model looks at the determinants of economic growth and the standard of living in the long run, the very long run. Let's begin by considering the differences and similarities between the Solow model and the classical model. we will have the same equation, income equals consumption, y is equal to C plus I plus G, but we're going to eliminate government. So we have a simplified supply equal demand equation. Y will just equal consumption plus investment. We're still concerned with equilibrium and how we get there, but we're going to call it a steady state. This is a fundamental perspective in economics in general. We try to define an equation for income, for consumption, for investment, define savings, and then figure out how equilibrium occurs. In this model, K is no longer fixed. Investment will cause the capital stock to grow, and depreciation will cause the capital stock to shrink. And in addition, labor is no longer fixed. We're going to have a population variable. Population growth will impact the capital stock as well, and the long-run potential of the economy. We will have no government, and so that means there will be no taxes as well. This is to simplify the model. We will analyze fiscal policy later, but for now we keep the model simple. We will also use new notation to create a model that is in per worker units instead of the aggregate magnitudes for the economy as a whole. So let's return to our production function. This says that aggregate output is a function of aggregate or total capital in the economy as well as aggregate or the total labor force. Let's divide both sides of the equation by total labor in the economy, capital L. This means that Y gives us output per worker, how much a representative worker in the economy produces. But we are also going to divide total capital, the input to the production function, by L as well. And this will give us total capital per worker. If we do the same for labor, of course, we just get 1. So our new function is output per worker and is a function of capital per worker. We can do this for production functions that are characterized by constant returns to scale, like our Cobb-Douglas production function. If we let Z equal 1 over capital L, in essence, we've defined a production function that is only a function of capital, or more specifically, capital per worker. Notice the notation of small letters to represent per worker units. Small f is a function of capital per worker. F of k is a per worker production function. It shows how much output one worker could produce using capital per worker units of capital. This is important, so I'm going to say it again. This is the same function we used before, but now we are looking at a production function that is a per worker output function. Here is our familiar production function graphed. This production function is using capital per worker, little k, as the input and producing output per worker, little y. Notice that the marginal product of capital is the slope of the production function, just as before. The slope is the rise over the run, where the rise is f of k plus 1 minus f of k, and the run is 1, for 1 unit of capital per worker. The function, like most production functions, exhibits diminishing marginal product of capital. That is, the production function is increasing at a decreasing rate. I can produce more output, say 4 more bushels of wheat, but as I add additional units of capital per worker, I will get a little less output each time. The next time I add a unit of capital per worker, I may only get 3 bushels of output. My output is still increasing, but at a decreasing rate. Now let's go back and remember our national income identity. Y is equal to C plus I. Remember, no government, so there's no G. And let's also put this in per worker terms. So output per worker is equal to consumption per worker and investment per worker. Little y is equal to little c plus little I. Supply still equals demand. And our national income identity still holds. Supply is equal to output, is equal to income, is equal to little y, is equal to little c, plus little I, which is equal to total consumption, which is equal to demand. It's the same thing, nothing has changed, except we've now translated all our equations into per worker units. Let's consider the consumption function. Remember that our consumption function told us that our income was divided between savings and consumption. So let's let little s equal the savings rate, or that fraction of income that is saved. Little s is an exogenous parameter determined by outside forces, like government policy, consumer preferences, or other institutional forces. Note that s is the only lowercase variable that is not equal to its uppercase version divided by L. It's just a savings rate. So our new consumption function is little c is equal to the quantity 1 minus s times output per worker. A simple consumption function, it is only some percentage of income per worker that is consumed. 1 minus the savings rate is the percentage of income consumed, or what is left over after savings. But we still need an investment function. Remember, in the classical model, we assumed that capital did not change. An output identified by the production function had capital stock as an input variable. But stock is a level of capital. Now we will let capital change. An investment will allow capital stock to grow, causing the capital stock, or level, to increase in each time period, say yearly. And as the capital stock increases each year due to investment, economic growth occurs. So investment is expenditure on new plant and equipment and causes capital stock to increase each year. Depreciation causes the capital stock to fall, but let's consider investment first. To do this, we begin with savings, because savings equals investment. By definition, savings is what is not consumed from income. This is just y minus c. But let's replace c with a consumption function from the previous slide. So we get that y minus c is equal to sy, which is equal to s times f of k. Savings function is sy is equal to s times f of k. Now let's find the investment function. From our national income identity, we can solve for I. I is just equal to y minus c, but from our previous equation up above, we know that y minus c is just s times y. And now we've shown that I is equal to s times y, which of course implies that investment is equal to savings, just as before. So the investment function becomes I is equal to s times f of k. This figure shows how for any value of k, the amount of output is determined by the production function. But we can also show how the allocation of that output occurs. Because sf of k represents that which is saved, this is what is allocated into investment. So the distance from the x-axis to the savings function, sf of k, represents investment. And the remainder is that which is consumed. So output is equal to consumption plus investment, or y is equal to c plus I. You might wish to pause this video and think about this. Convince yourself that y is equal to c plus I here, as it will become important later. Notice that the real interest rate r does not appear explicitly in any of the Solow model's equations. The investment still depends on r, the interest rate, which adjusts behind the scenes to keep investment equal to savings at all times. Now we move on to how capital can diminish or shrink. Remember, what is different in this model is that we must allow for capital to change, This is important because we will argue that it is ultimately investment that allows an economy to grow, and depreciation causes it to shrink over time. If the economy does not grow, then capital depreciates more than businesses invest. So we will let delta be the depreciation rate and assume that it is between 0 and 1 and represents the fraction of capital stock that wears out each year. Depreciation is some portion of capital and must be replaced every year. For example, if capital lasts on average 25 years, then the depreciation is 4%, and delta is 0.04. The total amount of capital that depreciates each year is 0.04 times K. Here is the graph of the depreciation of capital per worker. Note that the slope of the depreciation function is delta. Now let's create an equation that explains how both depreciation and growth can occur in the capital stock. The basic idea is that investment increases capital stock and depreciation reduces it. The change in capital stock is going to equal investment minus depreciation. Or in other words, delta K is equal to I minus delta K. Now the delta associated with the change in capital stock is an uppercase delta in Greek, and the depreciation delta is a lowercase delta in Greek. But we also know that I is equal to S times F of K. So our capital accumulation function becomes delta K is equal to S F of K minus lowercase delta times little k. Now, the change in capital is called the capital accumulation function because it tells us how much capital stock is added to each year. This capital stock is added to the previous capital stock from last year. The capital accumulation function is the equation of motion for K, and it's the Solow model's central equation. It is the equation for the motion of K as it determines the behavior of capital over time, year after year, which in turn determines behavior of all the other endogenous variables in the system, because they all depend on K. The steady state is the point at which capital stops growing, or where delta K is equal to 0. When delta K is equal to 0, that implies that S times F of K is equal to delta K, and investment is just enough to cover depreciation. And then capital per worker will remain constant. Delta K will always be 0 at this point, and it occurs at one value of K. We denote that as K star, and we call it the steady state capital stock. Let's look more closely at the equation of motion and see what is meant by it. This figure shows us the investment and the depreciation for given levels of capital stock. Consider K1 on the x-axis. For this amount of capital stock, we can see what is the level of investment I and the level of depreciation delta K. The greater the capital stock K, the greater is output and investment, but also the greater the depreciation as well. Notice that at K star, investment just equals depreciation. We call this point where investment is equal to depreciation the steady state level of capital. The change in capital stock is exactly 0 here. It is no longer accumulating, nor is it depreciating. At this point, both the capital stock and output are steady and not changing. It is called steady state because there are forces in the economy that keep the economy here. The steady state is important for two reasons. First, the economy will stay there, just like equilibrium in the classical model. If the economy is not there, forces will kick in that will move the economy there. For example, suppose that the economy is at K1. The economy will be moving toward the steady state since investment is greater than depreciation. And if the economy is at K2, depreciation is greater than investment, so the economy will shrink until it arrives at K star, where investment is equal to depreciation. The steady state represents long-run equilibrium for an economy. The steady state is the point at which capital stops growing, or where delta K is equal to 0. When delta K is equal to 0, that implies that S times F of K is equal to delta K, and investment is just enough to cover depreciation. And then capital per worker will remain constant. Delta K will always be 0 at this point, and it occurs at one value of K. We denote that as K star, and we call it the steady state capital stock. So as long as K is less than K star, investment will exceed depreciation, and K will continue to grow toward K star. Now you try. I recommend you do this. Try approaching K star from above. Draw the Solow model diagram and label the steady state K star. And then on the horizontal axis, pick a value greater than K star for the economy's initial capital stock and label it K1. Show what happens to K over time. Does K move toward the steady state or away from it, and why? Let's go through a numerical example with a specific production function. Let's suppose we have a production function in the aggregate. Y is a function of both capital and labor. And let's use the square root production function, the square root of K times L, which is equivalent to K raised to the 1/2 times L raised to the 1/2. Now let's derive the per worker production function by dividing through by L. We do a little bit of algebra here, so we have Y over L, and we do some cancellations on L and end out with K over L, all raised to the 1/2. Now let's substitute little y for Y over L and little k for K over L. And what do we get? A new production function with per worker units. We have output per worker is a function of capital per worker, and it's equal to the square root of K. Now let's assume that the savings is 0.3, little delta, or depreciation, is 0.1, and we start out with an initial value of capital per worker at 4.0. The Solow model equations are below. Output, or the production function, the consumption function, investment and savings function, depreciation, and capital yearly accumulation. The job is to find the steady state K star, and we do that by setting delta K equal to 0 and solving for K. Here I have calculated the first 2 years of capital accumulation using the equations from the previous slide. Notice importantly that each year you must calculate all equations based on an updated capital stock variable K. Be sure to add delta K, calculated from the capital accumulation equation, to the initial capital stock K. So in year 1, capital stock is 4, but in year 2 it is 4.2, since the capital accumulation in year 1 is 0.2. Here I have calculated the first 2 years of capital accumulation using the equations from the previous slide. Notice importantly that each year you must calculate all equations based on an updated capital stock variable K. Be sure to add delta K, calculated from the capital accumulation equation, to the initial capital stock K. So in year 1, capital stock is 4, but in year 2 it is 4.2, since the capital accumulation in year 1 is 0.2. Here are the values for year 1 and year 2 that I calculated on the previous slide. And here are the rest of the equations. I highly recommend that you calculate at least one row of these values for yourself. So how do we solve for the steady state? Well, we set delta k equal to 0 and then we solve for k. So we will continue to assume that s is equal to 0.3, delta is equal to 0.1, and the production function is the square root of k. We'll use the equation of motion to solve for the steady state values of k, y, and c. By setting the capital accumulation equation to 0, this implies that SF of k star is equal to delta k star. And so now we're going to plug in the relevant equations. S for 0.3, f of k star is the square root of k star, and so what we have is 0.3 times the square root of k star is equal to 0.1 times k star. Now we solve for k star, and this takes a little bit of algebra. We'll divide both sides by 0.1 and get 3 times the square root of k star is equal to k star, and now we divide both sides by the square root of k star, or k star to the 1/2, and we get 3 is equal to k raised to the 1 minus 1/2 star, and this of course implies that 3 is equal to k to the 1/2, and now we will square both sides and we get 3 squared is equal to k star, or 9 is equal to k star. Of course, this implies that y is equal to the square root of k star, which is equal to 3. So we now have y at the steady state. And finally, we solve for c star, which is equal to 1 minus s times y star. And so this is nothing more than 0.7 times 3, which is 2.1. This concludes part 1 of economic growth, the Solow Growth Model, Capital Accumulation, and the Steady State. In part 2, we will learn how a country's standard of living depends on its savings rate. We will apply the use of the golden rule to the growth model to determine the optimal savings rate and capital stock. We will then describe the transition process of moving the economy to the golden rule steady state using policies that impact the savings rate. This is Professor Ann Orion Spehar from the University of Alaska Southeast.